Dan Perry here with another digital electronics tutorial for Dan on Tech. In this video we'll be looking at sine or at analog and digital waveforms, specifically the sine wave, and talking about some of the terminology with that waveform. Well, if we start looking at a sine wave, and this holds true for digital waveforms as well, sine wave is an analog waveform. And if you look at where the top of the wave or the maximum value of the wave is, the amount or the distance between that maximum value and the top is the amplitude. And that's actually the max amplitude. Now, if you measure it at any point, that would be the amplitude or the height of that waveform at that point in its cycle. But the top value, the very top value, that is the maximum amplitude of that wave. The period of a wave is the time it takes for one complete waveform, so say from the top of the waveform to the top of the wave, or in this case if we look at, say, when it goes through zero till the next time it goes through zero, both in this case ascending or increasing, that's one complete waveform. Now, the wavelength, we use a lambda, Greek lambda for the wavelength, that's equal to the distance it travels for one complete wave. The frequency of the waveform is actually equal 1 over that wavelength, or lambda, and we talk about waves, or we'll talk about waveforms in terms of their frequency, and normally when we talk about frequency we talk about it in a unit we call hertz, or Hz, hertz or cycles per second. So if a waveform is at 100 hertz, that's 100 cycles per second. When we start talking about, for example, radio waves, if your local radio station may be operating at maybe a frequency of 101.5, that's 101.5 megahertz, or million cycles per second. Now with digital waveforms we still have the same thing. We have an amplitude, but that amplitude is typically a fixed value, or that it's either a zero value or it's a maximum value. Some digital waves just go from 0 to a max value. Others have a max and a min value, as we see in this second drawing. We still have a wavelength of a complete waveform here. And we have a frequency, and we calculate the frequency the same way. Now, this middle waveform is actually symmetrical in that it looks the same on both sides of it, top and bottom. This next one down here is not symmetrical. We're taller, or we're spending less time at the high value, the positive value, than we are at the low or the negative value. And you'll see that in digital signaling. Now, the next thing I want to look at is sampling of analog signals. And when we look at sampling of analog signals, what we're going to do is we need to measure periodically when a signal occurs. So if I come in here and I have a waveform and I want to digitize it, or I want to convert it into a digital signal, I have to take measurements at different times, or samples. Those samples that I'm taking will help me, or will be what we use to reconstruct the signal later on. And in this wave, we've got some points here where we sampled the signal periodically, and the samples are what we'll record. When you record, or when you play a CD, what you're doing is you're playing that sampled signal, that digital waveform that was captured, or those digital signals, and then it's reproduced as an analog waveform. Now, the more frequently we do samples, the better we'll get. So if, let's say we took a sample here at the beginning, let's say the next sample we took was here, and maybe one here, and maybe one here, and there, the digital signal that we would come up with for this one would be something like this. And when we tried to reproduce that, we would not get a very good waveform from it. So we have to worry about, when we're sampling signals, that we actually get a sample that is good. So let me clear this out. And now if we look at the wave, if we look at what we've done sampling this one, we would have a wave here, then let me do this. Wave here, then we'd come up to here, then here, down to here, down, then down here. And if we look at this one, our waveform actually looks better. It looks more like what we started with. That may be good enough for what we need, enough samples, but if we were to increase the frequency and take maybe twice as many samples, we would get a digital waveform that had a lot more data points and gave us a much better signal. So when you are taking analog signals and you're converting those analog signals into digital signals, we have to worry about how often we measure it so that we get a good signal, a good sampling. If we get a bad sampling, if we don't have sufficient data points, just like in that first one I drew, we'll end up with a bad reproduction. So thank you for watching this Dan on Tech video. Please subscribe to this playlist so you don't miss any future videos. Also, please check out and subscribe to our other Dan on Tech channels and playlists. Thank you.